You know gradient descent. Of course you do. You've written the code. You've probably typed this exact line 100 times. New weight equals old weight minus learning rate times gradient. It's the first thing you learn in machine learning. It's simple, it makes sense, but it's not what powers modern AI. Look inside any state-of-the-art model, any high-performance training script, and you'll find one name over and over and over again. Adam. And you're told to just use it, right? It's the default. It's just better. But why? Why is it better? So you look it up. You go to the paper or a blog post, and you're hit with a wall of math. But listen, give me 30 minutes. That's all I ask. And I will make the Adam optimizer click forever. Look at this. This is the Adam algorithm. We've got the first moment, called momentum, with all its M's and G's, then the second moment for the adaptive learning rate, then this weird bias correction step, and finally this massive update formula at the end. It looks crazy, but I promise you, you will understand why each piece exists. You will understand the exact problem it solves, and how they all fit together to create the most powerful optimizer we have today. Let's get started. To build Adam, we first need to understand the problems it was designed to fix. And that brings us to the first fundamental flaw of basic gradient descent. The core problem is that gradient descent is memoryless. Think about it. At every single step, it calculates the gradient and takes a step. That's it. It has zero recollection of what happened in the previous step. So as it gets closer to the minimum, the gradient shrinks. This means its steps get smaller and smaller and smaller. It slows down dramatically, just crawling towards the finish line. Let's make this painfully concrete. Here's our problem setup. We'll use the function f of p equals p squared. The gradient is just f prime of p equals 2p. We'll start way up at p equals 10 with a learning rate of 0.1. And now let's introduce our villain, standard gradient descent. The algorithm is exactly what you'd expect. For each iteration, the gradient equals 2 times the parameters, and then the new parameters equal the old parameters minus 0.1 times that gradient. Now, watch what happens. Take a look at this table. At iteration 0, we start at p equals 10. The gradient, 2p, is 20. The update, which is 0.1 times the gradient, is 2. So our new p is 10 minus 2, which is 8. Okay, iteration 1. We're at 8. The gradient is 16. The update is 1.6. And our new position is 6.4. You see the pattern here, right? We go from 6.4 to a gradient of 12.8 to an update of 1.28. I won't read the whole table, but look at that update column. The step size is constantly shrinking. This is deceleration. The algorithm gets less effective with every single step it takes. This is the problem we need to fix. So, how do we give our algorithm memory? We give it velocity. Imagine a ball rolling down a hill. It doesn't just stop and recalculate at every instant. No, it builds up momentum. It accelerates it. And that brings us to our hero, gradient descent with momentum. Let's look at the logic. We initialize velocity at 0. Then, for each iteration, we calculate the gradient just like before. But here is the key change. We say velocity equals 0.5 times the old velocity plus the new gradient. Then we update our parameters using that velocity, not the raw gradient. Now, let's see what a difference this makes in our table. Same setup. Iteration 0. P is 10, gradient is 20. The old velocity was 0, so the new velocity is simply 0.5 times 0 plus 20. Our new P is 8. So far, so good. But look at iteration 1. We're at P equals 8. The gradient is 16. The new velocity is 0.5 times our last velocity, 20, plus the new gradient, 16. That gives us a huge velocity of 26 factorial. We take a much bigger step and land at 5.4. Let's do one more. At p equals 5.4, the gradient is 10.8. The velocity becomes 0.5 times 26 plus 10.8, which is 23.8. You can see how the velocity is carrying over strength from previous steps. By iteration 4, we're already at 0.084. Time for the showdown. Standard gradient descent after 5 iterations is still way up at p equals 3.277. But with momentum, we are already at p equals 0.084. We're practically at the minimum. The algorithm used its memory of the first step to accelerate through the second. This is controlled acceleration. Now, that was a simple example, but this is where momentum's true power is revealed. Let's revisit that ravine problem. In a complex loss landscape like this, momentum performs 2 critical jobs at once. 1, it accelerates. Down the shallow valley floor, where the gradients are small but consistent, momentum builds up speed and makes progress much faster. 2, it dampens. This is the clever part. Across the steep walls of the ravine, the gradient is huge, but it's constantly flipping sign, causing that wasteful zigzag. But when momentum averages these opposing gradients, they cancel each other out, stopping the zigzag in its tracks. Momentum intelligently uses its memory to navigate more efficiently. It's just better. So we solved the direction problem with momentum. Our optimizer is smarter. It accelerates. It dampens. It's a huge upgrade. But it's still handicapped. Here's the thing. The core problem is that we are still using a single global learning rate for every parameter. But what happens when one parameter is extremely sensitive and another is incredibly stubborn? We're about to find out. Let's introduce our new enemy, an unbalanced function. Look at the gradient vector for this function. The partial derivative with respect to p0 is 100 times p0. The partial derivative for p1 is just 2 times p1. The gradient for p0 is 50 times stronger than for p1. p0 is sensitive. A tiny nudge will send it flying off a cliff. Meanwhile, p1 is stubborn. It barely wants to move at all. A single learning rate is destined to fail here. Let's prove it. We'll start with the villain, naive gradient descent. To stop our sensitive p0 from exploding, we're forced to use a tiny learning rate. We have no choice. Let's try 0.01. The logic is simple. For each iteration, we calculate the gradient and then subtract a tiny fraction of it from our parameters. Okay, let's look at the table. We start at p equals 1.5, 10.0. In iteration 0, the gradient is 150 for the first parameter and 20 for the second. The update for p0 is 1.5, so our new p0 is 1.5 minus 1.5, which is 0. It converged in one step. Perfect. But look at page 1. Its update is only 0.2, so it goes from 10 to 9.8, then to 9.6, then 9.4, then 9.2. This is just painful. Let's analyze this failure. The learning rate of 0.01 was perfect for p0. It converged in a single step. It couldn't have been better. But that same rate is cripplingly small for p1. Its progress is a miserable crawl. This is the definition of inefficiency. We need to give each parameter the learning rate it deserves. And that brings us to our hero, Adagrad, which stands for Adaptive Gradient. The idea is brilliant. Adagrad gives each parameter its own unique learning rate that adapts over time. How? It divides the learning rate by a running total of all past squared gradients. Let's look at the algorithm. We'll start with a new variable g squared, which is just an accumulator for each parameter, initialized to 0. For each iteration, we calculate the gradient like normal. Then, here's the key step. We add the gradient squared to our g squared accumulator. Finally, our adapted learning rate is our base learning rate. Let's use an aggressive 1.5, divided by the square root of that g squared accumulator. Then, we update the parameters. Okay, Adagrad in action. Look at this table. Let's focus on iteration 0. Our p is 1.5 and 10. The gradient is 150 and 20. So, g squared becomes 150 squared, which is 22,500, and 20 squared, which is 400. Now for the magic. The effective learning rate is different for each parameter. For p0, it's 1.5 divided by the square root of 22,500, which is 0.01. For p1, it's 1.5 divided by the square root of 400, which is 0.01, 0.075 factorial. The update becomes 1.5 for both, and our new p is 0.0 and 8.5. Look at the progress. After just a few steps, p1 is already down to 6.17. Let's analyze this success. Look at the sensitive p0. In step 0, its gradient was 150. Its effective learning rate was 1.5 divided by the square root of 150 squared, which comes out to exactly 0.01. Adagrad automatically discovered the perfect, tiny learning rate all by itself. Now look at the stubborn p1. Its gradient was only 20. Its effective learning rate was 1.5 divided by the square root of 20 squared, which is 0.075. This is 7.5 times larger than the learning rate used by naive gradient descent. It gave the stubborn parameter the aggressive push it needed. Time for the final showdown. After 4 steps, naive gradient descent got the stubborn parameter p1 down to 9.22. Adagrad, in the same number of steps, got it down to 617. It is converging dramatically faster. Problem solved. We now have a mechanism for adaptive, per-parameter learning rates. But in solving this problem, we've created a new one. A fatal flaw. Look at Adagrad's g-squared accumulator. In step 0, it was 22,500 and 400. By step 3, it grew to 1,100. This sum only ever increases. It never goes down. What do you think happens after a million training steps? The denominator will grow so large that the learning rate for all parameters shrinks to effectively 0. Learning just stops. This is known as the dying learning rate problem. So, how do we get the power of an adaptive learning rate, but one that doesn't just die over time? This is the moment we've been building towards. This is Adam. All right, here it is, the final boss, the complete Adam algorithm. On the screen is the full blueprint. First, we initialize a few things. M equals 0, which is our first moment vector, think of it as momentum. V equals 0, that's our second moment vector for the adaptive learning rate. And T equals 0, our time step counter. Then we loop for each training iteration. We increment our counter T, we calculate the gradient, G sub T. Then we have these 2 lines to update what are called the biased moment estimates. Then 2 more lines to compute the bias corrected estimates. And finally, we update the parameters. I know it looks complex. Seriously, I get it. It's a wall of symbols. But I promise you, by the end of this section, every single line will not only make sense, it will feel obvious. Now, let's break down this machine piece by piece. The core component is what I call the forgetful average. This is the brilliant idea that solves Adagrad's dying learning rate. It's called the exponentially weighted moving average, or EWMA for short. The formula is actually pretty simple. The average at time t equals beta times the average at time t minus 1 plus 1 minus beta times the new value at time t. So let's really understand beta, the memory factor. If you have a high beta, like 0.99, you keep a lot of the old average. This means it has a long memory and changes very slowly. But if you have a low beta, say 0.1, you discard most of the old average. It has a very short memory and reacts super quickly to new information. This forgetful property is the key. Instead of remembering every gradient from the dawn of time like Adagrad did, Adam will keep a running average that gently forgets the distant past. Now, let's look at the algorithm again with this new tool in our belt. Here's the Adam machine. Let's start with line 1, the direction engine. The formula is m sub t equals beta 1 times m sub t minus 1 plus 1 minus beta 1 times g sub t. So what is it? The paper calls it the first moment estimate. But what it actually is just momentum. It's the EWMA of the gradients, tracking the average direction. Beta 1 is the memory factor for that direction. It's usually high, something like 0.9, to make sure we have a nice, stable trajectory. Okay, next, line 2, the adaptive learning rate engine. Here, the formula is v sub t equals beta 2 times v sub t minus 1 plus 1 minus beta 2 times g sub t squared. What is it? The second moment estimate. And what it actually is an improved Adagrad. It's the EWMA of the squared gradients, which tracks the average magnitude. Beta 2, the memory factor for magnitude, is usually very high, like 0.999, because we want a very stable adaptive rate. Now for lines 3 and 4, the startup correction. So here's the problem. At the very start of training, M and V are initialized to 0. This means their first few estimates are biased towards 0, which causes tiny, slow, inefficient steps at the beginning. The solution? This is bias correction. Look at the formulas. M hat sub t equals m sub t divided by 1 minus beta 1 to the power of t, and the same for v. That term, 1 minus beta to the power of t, is small at first, which boosts the estimates. But as t gets bigger, that term approaches 1, and the correction just turns itself off. It's pure engineering. So clever. And this brings us to line 5, the final update. This is the payoff. All the components come together. The formula is theta sub t equals theta sub t minus 1 minus eta times m hat sub t divided by the square root of v hat sub t plus epsilon. Let's break that down. The step direction is from our smooth momentum estimate, m hat sub t, and the step size for each parameter is individually scaled by the square root of v hat sub t. It's the perfect synthesis. The smooth direction of momentum combined with the per-parameter adaptivity of a smarter Adagrad. And that's it. That's the whole machine. Adam runs 2 intelligent, forgetful averages, one for direction, one for magnitude. It corrects their initial bias, and then performs a single, robust, and adaptive update. Theory is great, but seeing is believing. We'll use the standard Adam parameters. Beta 1 is 0.9, and beta 2 is 0.999. Let's walk through the first iteration, step by step. The initial state is p equals 10, and our moments, m sub 0 and v sub 0, both start at 0. Okay, step 1. Compute the gradient. That's easy. The gradient g is 2 times p, so 2 times 10 is 20. Step 2. Update the first moment m. The formula is m sub 1 equals beta 1 times m sub 0 plus 1 minus beta 1 times g. Plugging in the numbers, that's 0.9 times 0 plus 0.1 times 20. So m sub 1 equals 2.0. Step 3. Update the second moment volume. The formula is v sub 1 equals beta 2 times v sub 0 plus 1 minus beta 2 times g squared. So that's 0.999 times 0 plus 0.001 times 20 squared, which is 400. That gives us a v sub 1 of 0.40. Step 4. Now for the bias correction for m. Remember this? M hat sub 1 equals m sub 1 divided by 1 minus beta 1 to the power of t. In this case, t is 1. So that's 2.0 divided by 1 minus 0.9, which is 2.0 divided by 0.1. That gives us a bias-corrected m hat of 20.0. Step 5. Bias correction for v. Same idea. V hat sub 1 equals v sub 1 divided by 1 minus beta 2 to the power of 1. That's 0.40 divided by 1 minus 0.999, which is 0.40 divided by 0.001. And that gives us a v-hat of 400.0. Step 6. Calculate the update. This is the big one. The update is eta times m-hat divided by the square root of v-hat plus epsilon. So 1.05 times 20 divided by the square root of 400. The square root of 400 is 20, so our update is 1.05 times 20 divided by 20, which is just 1.05. And finally, step 7. Update the parameter. P new equals our old p minus the update. That's 10.0 minus 1.05. Our new p is 8.95. Let's look at the result of that first iteration all laid out. Our new p is 8.95. We moved closer to the minimum. Gradient descent exploded, but Adam took a calm, measured step in the right direction. Now, we're not going to walk through every single calculation for all 10 iterations, but here is the full table. Just look at that new p column. It goes from 10 to 8.95 to 7.91, 6.93, 5.99, all the way down to 0.95 after just 10 steps. You've made it. We started with a simple, flawed idea of gradient descent, and we systematically solved its problems one by one, building our way up to the complete Adam optimizer. You have just mastered the core logic behind modern optimization. This wasn't a random walk through a bunch of equations. It was a logical engineering journey where each new idea was built to solve a specific, concrete failure of the last. Let's lay out that entire journey from start to finish. Look at this table. It's the whole story. First, the problem of inefficient direction and oscillation. The solution? Momentum. The key idea was to average past gradients to find a better, smoother direction. Second, the problem of an inflexible, one-size-fits-all learning rate. The solution was Adagrad. The brilliant idea was to give each parameter its own learning rate based on its history. But then, problem number 3. Adagrad's learning rate dies. So what was the solution? Forgetful averages, the exponentially weighted moving average. We replaced the permanent sum with a moving average that forgets the distant past. And finally, our fourth problem. Those initial steps were too small because of the zero initialization. The elegant solution? Bias correction. We just corrected the initial bias of the moving averages to get a faster, more accurate start. This is the entire story. Adam is not a single complex idea. It is the synthesis of these 4 solutions. It uses an EWMA of gradients for direction, which is the soul of momentum. It uses an EWMA of squared gradients for a per parameter adaptive rate, which is the soul of Adagrad, but without the fatal flaw. And it uses Biascore to make sure the whole system starts up smoothly. The result is a robust, high-performance algorithm that automatically adapts to the unique challenges of a complex loss landscape.